Question 13 from Paper 1 of the 2022 Higher Physics exam from the SQA. The following statement represents part of a radioactive decay series. Nucleus X undergoes alpha emission to produce nucleus Y, and nucleus Y then undergoes beta emission, and we end up with 21483 bismuth. And we asked to find out what nucleus X is. Before we start, let's look what happens with an alpha particle. An alpha particle has got a mass number of 4 and an atomic number of 2. What does this mean? If a nucleus ejects an alpha particle from itself, it's going to lose 4 from its mass number, and it's going to lose 2 from its atomic number. What about the beta particle? Have to be careful here. The beta particle has got no mass and -1. So what happens there? Well, if a nucleus releases a beta particle, there's going to be no change to its mass number, but its atomic number is going to increase by 1 because you're throwing away a -1, which is the same as actually gaining 1. So to do this, we start with nucleus X, and we give it a mass number of A and an atomic number of B. And we know from algebra that if we emit an alpha particle from there, we're going to have nucleus Y, and it's going to have a mass number of A minus 4, because you're going to lose 4 from the mass number when emitting an alpha particle. And the atomic number, you're going to lose 2. It's going to have B minus 2. And then in turn, you're going to have the Y nucleus emitting the beta particle. This is where you have to be careful, to give you the nucleus Bi, which we'll just call Z for the moment, just to give it a parking place here. When this nucleus emits a beta particle, its mass number remains unchanged, so it's going to be A minus 4. And the B minus 2, the atomic number, is going to gain 1, which is going to be B plus 1, because B minus 2 plus 1 is going to give you B minus 1. Now we compare that to our final product, which is going to be 214 bismuth and 83. We can see that we have got A minus 4 is equal to 214. That's the equivalence over here. So therefore, we can say that A must be equal to 218. If we make the equation up, A minus 4 equals 214. So we now know that A is 218. What about B? Well, we know that B minus 1 should equal 83, and therefore B should be equal to 84. So our original nucleus will have the following for its mass number and for its atomic number. It will have 218 for its mass number, and it will have 84 for its atomic number. So we look very carefully at the list we've been given. You can see 218, 218, and there's 21884. In fact, X is polonium. So our answer is C. Question 14 from Paper 1 of the 2022 Higher Physics examination from the SQA. The following statement represents a nuclear reaction. You can see 24094 plutonium. It's going to react to give you U236U92 plus helium, alpha particle given off of 42. Now the total mass before the reaction is 398.626 times 10 to the minus 27 kilograms, and the total mass of the particles after the reaction is 398.615 times 10 to the minus 27 kilograms. And you can see we have lost mass. This mass has been lost, but it really hasn't been lost. It's been changed into energy according to the energy formula, E equals mc squared. It is up there, E equals mc squared. So all we have to do is find this mass defect. So we can say that the big number is 398, so we put that down, 398.626 times 10 to the minus 27 kilograms, and we subtract the bottom number, which is 398.615 times 10 to the minus 27 kilograms. So we take the bottom number away from the top number, we're going to be left with 1.1 times 10 to the minus 29 kilograms. If you do that in your calculator, and that is the mass defect. That's how much mass has been changed into energy according to Einstein's famous equation, E equals mc squared. So all we have to do is just say put the mass into that equation and multiply it by the speed of light squared. So the energy released, E, is going to be equal to the mass times c squared, which is going to be equal to the mass released 1.1 times 10 to the minus 29 kilograms, and we multiply that by the speed of light squared, 3 times 10 to the power 8 all squared. Now the answer we get from that comes out to be 9.9 times 10 to the minus 13 joules. It's a straightforward, simple arithmetic of physics, looking at the mass defect, the mass lost in the reaction, and putting the mass into Einstein's equation equals mc squared. And we get a value of the energy released is going to be 9.9 times 10 to the minus 13 joules, which is going to give us answer D. Question 15 from the 2022 Higher Physics Examination from the SQA Paper 1. The irradiance of light incident on a surface from a point source is 20.0 watts per metre squared. The distance between the point source and the surface is 5 metres. Now the point source is now moved to a distance of 25 metres from the surface, and we have to find the new irradiance of the light incident on the surface, and we're given our 5 choices. Well, from our data book we know we're going to always have this equation here. The irradiance I is going to equal to a constant value divided by the distance squared, and the distance is the distance the light source is away from the particular surface that we're measuring the irradiance on. Now because of that particular form, we can cross multiply and we can say I d squared is going to equal to a constant. That K stands for a constant number. Now what this really means then is that the first irradiance times the first distance away squared will always be equal to the same number as the second irradiance times the second distance squared. So that's the kind of equation we have to use here. So we know that I1 is going to be equal to, in this case, 20 watts per metre squared, and we know that D1 is going to be equal to the first distance away, which is 5 metres, 5.0 metres, and therefore we also know that I2 is what we're after, so put a question mark here, and the distance D2 is going to be equal to 25.0 metres away. So to find the irradiance I2, you can see if we do a wee bit of rearranging, I2 has got to be equal to I1 D1 squared, and always remember the squared part there, divided by, in this case, D2 squared. So just put in the numbers. I1 is going to give you 20, just keep to 20 now, times 5 squared, which is going to give us 25, divided by D2 squared, which is 25 squared. So we do that in our calculator, we end up with 0.8, and of course the units for irradiance is going to be watts per metre squared. It's a straightforward irradiance calculation. So our answer to that one is going to be 0.8 watts per metre squared, and it's going to be equal to part B, letter B.